Logarithmic and exponential equations. What we're going to do is look at solving some logarithmic equations and applying all the other properties we've been learning about logs. So let's just jump into the first example. Solve the equation. And it says log base 6 of 2x minus 6 equal to 3. Best advice I can give you is if you are faced with a log equal to some value, then try, and you can't do anything else with it, then change to an exponential and see if that helps you out. So I'm going to start with this base 6. I'm going to loop around until I come around this way. And that's going to give me 6 to the third equal to 2x minus 6. So changing this from a log to an exponential helped me because my goal is to get this x by itself. And I'm going to be able to do that in this form more accurately. So let's see, 6 cubed is 216. And so I'm going to add 6 to both sides. That gives me 222 equal to 2x. And divide by 2. So x is equal to 111. In this next example, it says solve the equation, and it says log of 50x plus 25 minus log x equal to 2. So similar situation, you have a log equal to a value, but in this case, I have log written twice. So my first step that I want to do is I want to condense this down so it only says log once. We're going to use our condensing property where we know that we can write this because they're both log base 10. Subtraction becomes division, so that gives me 50x plus 25 divided by x equal to 2. So I just condensed down that left side. But now I'm back to where I was before in equation number 1. I have a log equal to a value. So if I can't do something with it, I'm going to change it up by changing it to an exponential. Now remember, this is base 10 if it's not written. So when I change this to an exponential, I'm going to get 10 squared equal to 50x plus 25 over x. Not really loving that division, so I'm going to multiply both sides by x to cancel it out. 10 squared is 100 times x, so I get 100x equal to 50x plus 25. I'm going to get all my x's together, so I'm going to subtract the 50x. Gives me 50x equal to 25, and then divide. So x is equal to 1/2. I'm just going to work many different equations and kind of talk about those steps or tricks or what do we need to do. So let's look at equation number 3. Solve the equation. So you can see I have one natural log going on right here. So let's see if we can isolate that. And then that may help us because we can do like we did in problems 1 and 2. So in order to isolate this, I'm going to go ahead and subtract the 5 from both sides. That gives me 4 ln of 5x equal to negative 3. This is multiplied by 4, so I'm going to divide both sides by 4. That gives me ln of 5x equal to negative 3/4. Now, here I can either kind of snell it around, change it to an exponential, or if you remember, e and ln are inverse properties of each other. So to cancel that ln, I'm going to e both sides. That means this would cancel, and I would be left with 5x equal to e to the negative 3/4, which is just a number. And my goal is to get this x by itself, so I'm going to divide both sides by 5. Now with this one, that's just a button in your calculator, e to the negative 3/4. So using your on-screen calculator, e to the negative 3/4, divide that answer by 5, and that gives me a value of 0.4234. Now, if it doesn't say give an exact answer and you get a decimal, then just round to an assumed 3 or 4 decimal places. So you can see in these examples, we're working with many different things here. And in working with them, we've got to kind of approach each problem differently. We need to analyze the situation and see what we can do with it. And sometimes that means doing small steps like you saw in this one of -5 divided by 4. Sometimes it means just changing up the format and turning it to an exponential. Let's look at this next property. It says solving exponential equations with the one-to-one property. So when we're solving exponential equations, meaning that we don't have log written here, but we do have a situation where we have the same bases, then what we're going to do is we're going to say, okay, because those bases are the same and they're equal, I can just set what the exponents are equal to each other. So like in this first example, 3 to the x plus 1 equal to 27. What we want to do is try and set these up so that they have the same bases. And so our goal with this one is we want to change to the same base. And so we can get it into this exponentials on both sides, and we can use that one-to-one property. And so I'm going to look at this and say, okay, 3 to the x plus 1, that's fine. But 27, could I turn that into a base 3? And remember, in all of this unit, we're looking at things being raised to a power. So if need be, go to your calculator and say 3 to the first, 3 squared, 3 cubed. And 3 cubed is what gives us 27. So because these are both base 3, then I can set their exponents, x plus 1 equal to 3. So I would say x plus 1 equals 3, and then I could just solve that out. So x is equal to 2. Now I'm trying to show you some equations where you can follow the logic so that when we get into harder situations, you don't have to think about logically doing it. You have a process, okay? So don't just play around with numbers like, oh, I'm just going to try some numbers and see how it works out. Let's work with the process. Change it into the same base so that you can set your exponents equal. Let's look at this next one. It says 1/2 raised to the x is equal to 8. So first thing I'm going to do, this is 2 to the first power. Rules of exponents, if I bring this up to the top, that gives me a 2 to the negative 1 raised to the x. And then by rules of exponents again, power to power, you multiply, so it gives me 2 to the negative x. Then let's focus on our 8. So again, using your on-screen calculator, you can say 2 to the first is 2, 2 squared is 4, 2 cubed would give me 8. So I'm going to say 2 cubed. So because now that I have base 2 and base 2, I can set their exponents equal. And I can say negative x is equal to 3. And then I can solve that out by dividing both sides by 1. So x is equal to negative 3. Again, just want to do some simple equations to get us going so that we can see those steps and processes kind of appeal to your logical side. And then when we go into some more complicated problems, we have steps and processes. Now let's look at this next one. It says given e to the m equal to e to the n when m equals x squared plus 12 and n is equal to 7x. And so we're going to have to set this up to start with. So they said that m is equal to x squared plus 12. So it means I have e to the x squared plus 12 equal to n, and they're defining n to be 7x. So I'll say e to the 7x. So you can see from this format here that I am definitely in that same situation. I have both are base e's, so they're the same base. So I'm just going to set these exponents equal. So I'll say x squared plus 12 is equal to 7x. When I see something like that, I can see I have a quadratic, so that means I want to move everything over to one side. That gives me x squared minus 7x plus 12 equal to 0. And then I could factor. Now, if you're not super sold on factoring, you could quadratic formula that. That would be negative 3 and negative 4. And so x minus 3 equals 0, so I get 3. And x minus 4 equals 0, so 4. So in this example, we had to pull up some of our quadratic solving skills paired with our one-to-one property. Okay, this next problem is where it comes into play of we don't want to just play around with numbers and take that logical approach because of this problem here. It says given 8r equal to 16 to the t when r is equal to x plus 2 and t is equal to x plus 1, find x. So I want to figure out, let's see, 8 to the r, let's rewrite this so I can visually see it. instead of r, we're going to say x plus 2, is equal to 16 to the t, and instead of t, we're going to say x plus 1. So this is our situation. Next, I want to turn this into a same base situation. So let's think about 8 and 16, and let's make those numbers smaller. Let's turn this 8 into a base 2. From earlier, we saw that 8 is equal to 2 cubed, but we are raising this to the x plus 2. And then we're going to look at that 16, and again, using your on-screen calculator, you could find out that 2 to the 4th is 16. So instead of 16, I write 2 to the 4th. So I've turned both of these into a base 2. Power to power, I'm going to multiply, so it gives me 2 raised to that, and I'll just distribute that 3. So 3x plus 6 equal to 2. Again, power to power, you multiply, so I just need to distribute that 4x plus 4. And now through a couple of steps, I can see that because I have the same bases with some work on my part, I can set these exponents equal. So I could say 3x plus 6 is equal to 4x plus 4. Subtract 3x, just solving for x here. That gives me x plus 4. And then subtract 4. So it gives me 2 equal to x. So you can see this one was definitely a little bit more labor intensive, but we were still able to use our processes and steps to solve it. So in this section, I just want to kind of show you what it looks like to solve exponential equations with one-to-one property. Let's look at this next part. It says solving exponential equations with logarithmic properties. If you have an exponential expression on one side, turn the equation into a log by taking the log of both sides. And so what we're going to do, our key takeaway with this one is we are going to be taking the log of both sides. But we're just going to work through some different examples and kind of see what these processes are going to look like. So it says solve the equation. So the first thing I want to do is I want to isolate the exponential. To isolate that, it's being multiplied by 3, so I'm going to divide both sides by 3. That gives me 2 to the x equal to 42 over 3. And this is where I can't just plug in numbers for x and go, oh, how am I going to get 42 over 3? I'm going to use my processes to help me with that. And so I'm going to work this 2 different ways, and then you just kind of stick with the way that you like the best. The first way is I'm going to take that 2 to the x equal to 42 over 3. And what I can do is I can log base 2 both sides. So I could say log base 2, as long as I do it to both sides, it's equivalent. And why would I want to do that? Because this is that inverse property. So that would give me x equal to log base 2 of 42 over 3. Now, I can't plug that in my calculator, so that's where it comes into play, the change of base formula. So that would be log of 42 over 3 divided by log of 2. Using my on-screen calculator, that gives me the equivalent of 3.807. Let me show you another way that we can solve this. And this is the neat thing about logarithms, how there's many different ways that you can work with a problem and still get the same result. And again, you just want to stick with the way that works best for you. Both are going to be mathematically correct. So let's start with this piece right here. 2 to the x equal to 42 over 3. And I should have in that first example 42 over 3, that just gives me 14. So let's work with that. I should have done that on option 1. If I want to solve this, you can see on the left-hand side, I chose to use the inverse property. Let's use the log properties and let's ln both sides. And this is kind of my go-to when I'm working with all these log problems on repeat. If I ln both sides, I have not changed the problem. I've just changed the way it looks, but mathematically it's the same because what I did to one side I did to the other. By your properties of logs, I can bring that exponent out front. That gives me x ln 2 equal to ln 14, and then divide both sides by ln 2. So x is equal to, I go on my calculator and I type in ln 14 over ln 2, and that also gives me 3.807. And so you're going to see me probably use that property a little bit more than the other one. because it comes in handy. You'll see in the next example. But either of these, you can see, got us the same answer. I showed my work. They're both mathematically correct. Let's look at this next problem. It says solve the equation. E to the 2x plus 5 is equal to 60. And so what I want to do is I want to first get the exponential by itself. So first I'm going to get this piece by itself. I'll do that by subtracting 5 from both sides. That gives me e to the 2x equal to 55. And this is why I would choose option 2 a lot of the times, because when I ln both sides, I'm beginning to see that ln e, which is an inverse property. And so ln e of 2x equal to ln 55. Ln e is an inverse property. It cancels. We also know exponents come out front. So that gives me 2x ln e equal to ln 55. But when that ln e cancels, it's becoming a 1. So really I have 2x equal to ln 55. And then divide both sides by 2. Now the key is you don't want to stress that ln 55 divided by 2. That's just a number. I type it in my calculator and that gives me 2.004. And so that ln property is really nice, not only in the first example, so we can move the exponent out front, but in this example because ln e equals 1, and so that's why that went away. Let's kind of keep working through some examples and see what we can do. So this next one, I have 3 times 3 to the 2t minus 5 minus 4 equal to 11. So again, same thing. I want to get this exponential by itself before I start using any of my log properties. So I'm going to add 4 to both sides. That gives me 3. 3 to the 2t minus 5 equal to 15. Divide both sides by 3. That gives me 5. And now I have that exponential by itself. And I'm back to example 1. I can either do an inverse property or ln both sides. I'm kind of a go-to on ln. So I'm going to ln both sides. So that's going to give me ln of 3 to the 2t minus 5 equal to ln 5. And then I'm going to move that exponent out front. So I get 2t minus 5, ln 3 equal to ln 5. And my goal with this is to get this t right here by itself. And so I would divide both sides by ln 3. So that gives me 2t minus 5 equal to ln 5 over ln 3. And I'm writing ln 5 over ln 3 because that's an exact answer. And then once I get through with my process, I'll go in and find that decimal number. If I use a decimal number early on in the problem, it means my result's going to be really rounded. And so then I would have to add 5 to both sides. That gives me 2t equal to ln 5 over ln 3 plus 5. And then divide both sides by 2. So t is equal to, I'm going to take this whole piece here and plug it into my calculator. And you can do it in steps. Do your ln 5 over ln 3, enter, answer plus 5, answer divided by 2. Or you can make it look just like this in your on-screen calculator. And that result will be 3.232. Now, these are a little bit harder, but hopefully from earlier conversations, you're getting those properties down and how to work through those. 2 more examples. Solve the equation. I have e to the 2x minus 2 e to the x equal to 24. Now, when you're looking at this, hopefully this is cueing you on that this looks similar to when we were solving quadratics earlier. And so when you're solving a quadratic, or in this case, a quadratic type equation, you want to get everything over to one side. So I'm going to subtract 24. That gives me e to the 2x minus 2 e to the x minus 24 equal to 0. You might be thinking, well, how did you know that was a quadratic? How do you know you're going to now take that and factor it? Let's take a little side note and think about this. E to the x times e to the x, that equals e, you have to add those exponents together, to the 2x. So when I'm going to factor that, that turns into an e to the x times e to the x is what would give you that e to the 2x. And then you can use your other factoring rules of what will multiply to give you negative 24 and add to give you that negative 2, and that's a negative 6 and a positive 4. I can then set these two equal. I get e to the x minus 6 equal to 0. E to the x plus 4 equal to 0. So I'll add 6 to both sides. Now I'm working with two smaller equations. ln both sides, that gives me x equal to ln 6. Just a number, I could plug that in my calculator, 1.792. Now over here, something funny happens. So I subtract 4 from both sides. That gives me e to the x equal to negative 4. I ln, and I get x equal to ln of negative 4. But with our rules of exponentials and our restrictions on our domain, or if you just go to your on-screen calculator, you'll learn this does not work out. We can't natural log a negative. And again, that goes into those domain restrictions that we looked at earlier with logs. And so in this one, although our process was looking like it was going to result in two answers, because of the natural logs and those restrictions on those domains, only one answer was going to work for this. And again, you could have gone to your on-screen calculator. It will not give you a value for ln of negative 4. Last example, let's see what we can do with this, and then you'll want to go and try those homework problems and reach out if you need some help. Now this one is a little bit more time consuming, but I wanted to kind of show you how this is going to work out. So earlier we looked at something called the one-to-one property, and we said if we can get those bases to be the same, then we can just make the exponents. But there is no way I'm going to turn 5 into a 4. 5 is prime, 4 is even. I am not going to get these to be similar bases and use that one-to-one property. But this is where natural logging both sides is going to come into play. If I natural log both sides, I get ln of 5 to the x plus 2 equal to ln of 4 to the x. By properties of logs, I can bring exponents out front. Just want to make sure I keep that one grouped. That gives me x plus 2, ln 5 equal to x, ln 4. Now my goal is to solve for x, and I have these x's right here and right here. So what I want to do is I want to collect all x's to one side. So that would give me, let's go ahead and maybe distribute this out. That gives me x ln 5 plus 2 ln 5 equal to x ln 4. Now I can gather everything over to one side because this has an x and this has an x. So I'm going to get them over here to this left side. So I'm going to have to minus the ln 4 to move that over. And I'm going to have to minus this 2 ln 5 to get it to the right side. This gives me x ln 5 minus x ln 4. Don't you dare go canceling on those pieces. Equal to negative 2 ln 5. Now from here, I'm going to factor. So I can pull that x away from those two, leaving me with ln 5 minus ln 4 equal to 2 ln 5. And then finally, I can get this x by itself. This is now multiplication, so I can divide by ln 5 minus ln 4. ln 5 minus ln 4. Those are two numbers. That's not just that you can do 5 minus 4. So what I'm going to do is I'm going to plug all this right here into my calculator, and that will finally give me what that elusive x is, which is negative 14.425. Whew, that put a lot of concepts together. I know that was a little bit more difficult, but go and attempt the homework. Reach out to your instructor if you need some additional help or resources.